An indicator is defined as a solution of a weak acid or a weak base in which the undissociated and the dissociated forms have different colors. We can write out a general equation for an indicator like this one here, where IN represents the indicator. So the undissociated form HIN will have a different color than the dissociated form IN minus. Now indicators will change depending on the pH that we're at. So these changes happen mostly because of Le Chatelier's principle. If we increase the H+ concentration, this is effectively decreasing pH. This would be in an acid. If we increase H+, our equilibrium is going to shift to the left so that the HIN form of the indicator, the undissociated form, is going to be favored. If we decrease the H+, basically what we're doing here is we would add OH-, because those OH- are going to react with H+ to make water, effectively reducing the H+ concentration in solution. This will increase pH. This is in basic conditions then. If we decrease H+, our equilibrium is going to shift to the right. That means that the dissociated form of the indicator is going to be favored. And so we would have the color change for the dissociated version. An example of this would be litmus paper. So if we take LiT to represent whatever the chemical structure is of that litmus paper, our undissociated form is a red color, whereas our dissociated form is a blue color. In an acid then, remember in an acid we're effectively increasing H+ concentration. It would shift our equilibrium to the right, meaning that LiT is favored, and it would be a red color. In a base, we're adding OH-, so we are decreasing H+ concentration. The LiT- version of the indicator would be favored, and we would see the color blue. Now our general equation, HIN, reacts to give H+ plus IN-. All of these are in the aqueous state. We can then write a Ka for this general reaction. It would be IN- times H+ divided by HIN. When equilibrium is balanced between the undissociated and dissociated forms of the indicator is exactly in the middle of its color change. In a titration, this is known as its endpoint, or a change point of the indicator. This would be when the concentration of IN- is equal to HIN. That means that we could simplify the above expression. If these were equivalent, then they would cancel each other out, and the Ka would equal to the H+. Or the pKa would equal to the pH. The endpoint of an indicator then is the pH at which it changes color. This happens when the pH is equal to the pKa. Your textbook gives some examples of different indicators and ones that are suitable for different titrations. If you have a strong acid and a strong base, a couple of indicators that would be appropriate might be phenolphthalein or methyl orange. A weak acid and a strong base, again, phenolphthalein might not be bad. Phenol red is also a good one there. A strong acid and a weak base, methyl orange and bromothymol blue. And a weak acid and a weak base, because there's not a significant change in pH at the equivalence point, there really is no suitable indicator to use here. What you should understand is relating indicators back to the pH range at equivalence for the different types of titration curves that we did, and looking at the changes of the endpoints within the indicator and what the color changes are.